Good day, good evening, and welcome to today's webinar. My name is Mark Cox, and I'm a Senior Communicator at INNIO. I'll be your host today. I'd like to welcome you to our webinar platform. You'll notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the Questions widget. Just type them into the box at the top left-hand corner of your screen and click Submit. We will allocate some time at the end of the session to address any questions or comments that you may have. Please use the yellow Help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. But now, please allow me to share a short presentation about our company, followed by today's presenters. INNIO is a technology company developing, manufacturing, monitoring, and servicing gas engines for power generation and compression solutions. Our Jenbacher products are specialized in power generation. Jenbacher's North America sales and service hub is headquartered in Houston, Texas. We also have operations in Wisconsin, as well as in Ontario, Canada. INNIO's global headquarters and core innovation center is based in Austria. Out of the more than 3,000 global employees, over 500 highly qualified engineers are focused on innovation. INNIO's Jenbacher business has around 1,700 employees around the world. The first Jenbacher gas engine was manufactured in 1957. In total, Jenbacher's success builds on more than 90 years of engine experience. So far, about 22,000 engines for power generation and CHP have been delivered worldwide. Well over 1,000 of these engines went to customers in North America. Today, INNIO runs manufacturing facilities with a total of 65,000 square meters, producing 5 product lines of high-tech engines with outputs from 200 kilowatts to as high as 10 megawatts. Our engines are known for overall efficiencies of 90% and more. Their durability, fast start capabilities, and the ability to run on a broad range of fuels. Jenbacher also offers a comprehensive set of lifecycle services. Jenbacher has always been a front-runner in the gas engine industry. In addition to a series of world's firsts in technology, business also has a history of growth in the U.S. What started with a small sales and service office in Boston 30 years ago has grown into a strong network of INNIO and distributor sales and service expert teams across the USA and Canada. Jenbacher engines meet our North American customers' needs with top reliability and performance, delivering total efficiencies of up to 95% in cogeneration mode. We offer established, field-tested designs, optimized, robust engine components, along with a proven monitoring and control concept. Our engines can run on natural gas, as well as a broad variety of renewable or waste gases. This makes them a great solution for reducing our customers' CO2 footprint. With the capability to run on hydrogen, the potential to save even more emissions in the future is becoming reality. Our service organization provides everything you need to profitably run your Jenbacher power plant. You choose your tailored level of support, and we will deliver everything from the digital myPlant asset performance management solution for optimized uptime and reduced lifecycle costs, all the way to remote as well as fast on-site service support. We also run a remanufacturing program for efficient overhauls and provide you with comprehensive conversion, modification, and upgrade packages to help you make the most out of your Jenbacher gas engine. Let's look at a few of the most popular Jenbacher solutions for North America. Most Jenbacher power plants run in CHP mode and use up to 40% less primary energy compared to conventional generation of heat and power. We offer innovative microgrid solutions for a stable 24/7 power and heat supply, even if cities face a blackout. With our innovative greenhouse solutions, We power and heat the greenhouses and clean the exhaust gas for use as fertilizer, promoting plant growth. Jenbacher-powered data center power plants deliver lower emissions along with fast start capability based on reliable pipeline fuel operation. Using the renewable wastewater gas in Jenbacher engines provides 100% of a sewage plant's energy needs and, in the long run, significant cost savings. With our hydrogen options, we are prepared for a CO2 neutral world, supporting you all the way through this time of transition. By choosing Jenbacher gas engines, you decide for a greener and more profitable future. INNIO, energy solutions, everywhere, every time.
And now it is my pleasure to welcome you to this webinar entitled Jenbacher North America Presents Food and Beverage CHP Solutions from Jenbacher Gas Engines. Today's presenters are Luis Ampudia and Christian Mueller. Today's webinar will run for approximately 1 hour, including about 15 minutes for question and answer. So please make sure to answer the survey questions found in the widget bar at the bottom of your screen, and don't forget to enter your questions. Now I'll hand over to Christian and Luis. Gentlemen?
Thank you, Mark. Good day to everyone. I'm Christian. As Mark said, I'm one of the senior sales managers for the Jenbacher North America business based out of Houston, Texas. And with me, I also have Luis. Luis? Okay, seems like his audio is still off. So yeah, also with me is Luis Ampudia, also sales manager out of Houston. And together we're going to host this webinar. And I'm going to start off here. Basically, the webinar's topic is Power Your Food and Beverage. And we're going to really look at those type of applications. And if we look at our agenda, first I want to do a little overview about the CHP technology, because ultimately that's what most of these type of applications use. Then we'll go more in detail into the application itself. We'll talk about some project arrangements, how a typical project could look like. We'll go through some case studies, and at the end have Q&As based on the questions you all entered in the chat. So first off, to set the framework for this presentation, I want to talk a little bit about CHP, which maybe is quite familiar to you. And this diagram just shows again, as a refresher, what a CHP system could look like, where you have at the core a gas engine, which turns gaseous fuels, natural gas, biogas, different types of gases into electricity. And at the same time, the heat output of the engine, the exhaust, is used to either recover heat in the form of hot water or steam, or potentially absorption chilling. And you also use the engine coolant, which comes out of the engine, and run that through a heat exchanger, which further increases the recoverable heat on a CHP system. If we look at, basically, as Mark alluded to in the introductory video, the separate generation of heat and power, where you purchase your power from a power plant, and also get your natural gas there and turn that into heat, and you compare that to an on-site combined heat and power solution using a gas engine, then really the main advantage is that overall increased energy efficiency. So you cut out the transmission losses, you cut out the inefficiencies of centralized power plants, which have large wasted heat components, and you really make use of more than 90% of your primary energy input. And that gives you that high overall efficiency, which results not only in, of course, saving emissions, but also in saving you cost. So that's the basic concept of why one does CHP. If we look at, just for reference, again, I mentioned CO2 emissions. Obviously, the CO2 emissions in the grid, which is here across the US in these red bars, it shows different regions in the US. The CO2 emissions of those different grids really depend on, of course, what is being used to generate electricity. If there's still a lot of coal or natural gas in there, or maybe more renewables, which obviously have a which decrease the CO2 footprint. But if we look on average, the CO2 output of a CHP system, which is marked there in that green line here of a 420 Jenbacher CHP, which is about 1.5 megawatts, then you can see that on average, the increased efficiency of using a CHP system decreases your carbon footprint versus purchasing the power from the grid. So there's really that opportunity as well. On the CHP economic side, if we do a total project analysis, there's really quite a number of factors which come into play here. First off is the use of heat. So either it could be combined heat and power in a traditional sense, where you put out, let's say, hot water or steam, or you might do trigeneration, where in addition to the hot water or steam, you also produce chilled water by running your thermals through absorption chiller. So you first have to look at what's your use of heat at your site, and for a food and beverage customer, that very well might be either in the form of hot water, steam, or chilling. Then you look at the economics in terms of the electricity and gas cost, which is what we call the spark spread. So the higher the difference, meaning the higher the cost of electricity which you purchase from the grid, and the lower your gas cost, be it natural gas, or obviously if it's biogas, then the cost is even lower because it's a waste gas. And the higher the difference is between those two, the better your spark spread, and the more efficient it is for you to produce your own power. Then we have to look at how are we going to run the installation. Is it grid parallel, meaning you're tied to the grid, or is it an island operation, meaning you might disconnect from the grid? And there might be reasons to do that. For example, if you want to save the costly interconnection, or if the power from the grid is unreliable, then you might want to completely disconnect and just run on power through the CHP system. You might also choose to do both, run in grid parallel normally, and when you have a blackout, you switch into island operation and run your own little, let's just call it microgrid, and produce your own power, which increases your resiliency, which is also very important for customers. Then if we look into the sizing of the project, we have to look at the electrical and thermal load curves. That's really the load profile, as we call it. So throughout the day, throughout the year, you'll have varying uses of both electricity as well as thermal loads, and you then try to match that to the output of the generators to determine the size and the number of generators. For that reason, it might sometimes make sense to have more than one. So you could run one generator in base load and turn on a second one during peak hours. Next factor to consider is, are we looking at an existing building or a new construction? So a new construction is always relatively easier, obviously, because you can incorporate the design of the CHP right from the start. If you're looking at an existing building, there might be more retrofitting. You'll have to identify a space which is suitable to house the generator. You'll have to look at, obviously, bringing in all the necessary utilities, the water, the gas, the electricity, so that you connect all that to your CHP and make sure that it properly is operating. So there's a little bit more, let's say, engineering involved in that. Then one factor, obviously, it is, after you have completed this analysis, is to determine the total capital expenditure you will need to install this system. So you would have the CHP equipment cost, which consists mainly of the gas engine generator, and then the associated balance of plant, all those auxiliary systems, the pumps, heat exchangers, radiators, emissions after treatment, potentially all those systems which are associated with the CHP unit to make the whole system run. On the operational cost, you look at your electric and gas utility interconnection cost as one factor, because there's a cost associated to connecting your unit to the electric or gas utility, and potentially if there's any investment incentives or grants which are available. On the O&M side, the main variables are fuel cost, the cost of consumables, which basically means oil or coolant, or urea if you have an SCR catalyst. That's let's say the fuel and lubricant cost. Then you have your scheduled maintenance cost, as well as equipment depreciation. So you then really start to prepare a financial analysis of the whole project, taking into consideration the OPEX and the CAPEX. On your cost savings side, you'll look at what's going to be your reduced electricity purchase from the grid, since you're now self-generating, your reduced heating cost by using the waste heat from the generators and saving natural gas in your boilers. Then the revenue from potentially exporting surplus electricity, especially if you're connected to a grid which has very high peak rates. There might be times when you're going to get a lot of money for exporting the power if the grid is basically needing more power to be injected into it, and you get very nice incentives for doing that, as well as potentially any operational incentives for putting in this highly efficient system. So overall, there's quite a bit of moving pieces which go into putting this together, such a economic analysis to make sure that the system works for you. That's also one of the services where we really can help you with and to help you put all that together. Now, if we look at it in a more simplistic view, all the things I talked about, this is just a very simplified graphic to visualize this. So let's say you have your gas engine generator, you have a certain CapEx, the capital expenditure for putting the system in, and just as an example, that would be resulting in a levelized cost of 2 cents per kilowatt hour if you were to take the whole cost of installation and then, of course, depreciate it over the life of the engine. Then there would be a fuel cost, which is associated with operating the engine. In this case, we use natural gas with about $4.7 per MMBTU, which is approximately the current price of gas. As many of you know, actually, natural gas has gone up quite a bit here recently. So as you can see here, immediately, the cost of fuel over the life of the engine actually is much more important than the capital expenditure, just in terms of ratios. So definitely fuel efficiency is one of the most important things to consider when evaluating the choice of engine. So that's on your cost side, the capital expenditure and the fuel, the two main things. The thermal energy value, basically your waste heat, also has a value. That's that light blue. So that brings down your cost again, because now you're basically saving natural gas for your boilers. So there's a certain cost to be associated with that, which offsets more or less the O&M cost, which is the green here. So overall, if we look at all those factors, then your levelized cost of electricity, in this case, would be 6 cents per kilowatt hour, just as an example. What this graph here doesn't show are other factors which come into play. For example, resiliency. So if you have downtime at your site due to something like what happened here in winter in Texas, then you could potentially have very high costs for downtime of your plant, which are in addition to the cost savings you have here. So things like resiliency sometimes are a little harder to quantify, but they definitely, for many of our customers, play a big role in the decision to put one of these CHP systems in, because they really then enable their plant to operate at all times. The one thing, of course, is to be said is the natural gas also has to be available. So as long as you have natural gas available, or even better, if you produce your own gas, if you have a biogas application, then that provides you the security of fuel as well. As Mark also initially mentioned, there are many applications where CHP can be used in. So obviously today we're going to focus on the food and beverage segment, but I also wanted to just put that out here because it shows really that gas engines are used in a variety of applications, be it on the utility side, be it on hospitals, universities, airport, municipal buildings, landfills, wastewater sites, in the oil and gas industry, for greenhouses. So there's a very diverse set of applications, each with their own requirements and different types of gases, different types of uses of power and heat, where these engines can be used. And Jenbacher has really had a very broad experience in all of these type of applications, and we also have some future webinars talking about some of these other applications as well. CHP as such is not necessarily a new technology. This map shows just an overview of different types of CHP sites, small and large, where you have a combined use of heat and power to produce that at site. And the top commercial segments really for the use of CHP have typically been hospitals, universities, and district energy systems, but we're seeing more and more industrial customers or food processing customers which are looking at CHP as well as an important part of their overall plant to be more resilient and more cost effective. With that, I want to hand over to Luis, who's really going to get into the food and bev applications and the case studies. So Luis, I'll be glad to have you take over from here.
Thank you, Christian. And I'm sorry, I was on mute. My name is Luis Ampudia, and I'm a Senior Sales Manager for INNIO Jenbacher in Southwest Eastern United States. So going into the food and beverage applications, sorry about that. There are many CHP applications by specific industry. Just to name a few, I have a list in which the dairy operations, for example, require a lot of steam, specifically because of pasteurization or ultra-pasteurization, and also require hot water for several of the processes. And they need also the absorption chillers because they need to cool down the milk from, if it is just pasteurization, it's about 63 degrees Celsius to 3 degrees Celsius. And this type of operations run usually on natural gas, but they also run on biogas if the manure waste is close by. So they could have great savings by utilizing CHP on their operations. I will touch bases with the dairy later on in more detail. In animal feed processing for pellets or extrusions, CHP is required because for the pelletizing process, you need steam in order to produce the pellet at relatively high pressure. Because the steam is also lost during the process, you need to heat new water in order not to go from zero in the boiler or the Hershey heat recuperation steam generator. So you can heat the water up to 85 to 87 degrees Celsius. Usually is feed with natural gas. Going back to the breakfast cereal industry, it is also highly demanded by steam and lots of energy at the same time, just like the industries like Kellogg's or similar. So in order to form the flake, it needs to go like a paste over drums that later on the other side, you have the flakes. Those drums are filled with steam, heating up the drum, and that steam is recirculated. The hot water is used basically for sanitation, and usually they don't have many waste, so it's natural gas. In the poultry and meat processing, the slaughterhouses, there is a lot of waste, a lot of blood, and a lot of abdominal contents that go out from the deceased or sacrificed animal. So the CHP is very good because they have high energy needs, and they need steam in, for example, in the poultry, they need steam to defeather the birds. The steam is lost in the process, or to dry the offal in order to produce chicken meal. They also have lots of needs for absorption, for chilled water, and that's where the absorption chillers come in. Most of these places have lots of waste, and they have wastewater treatment plants that produce, or covered lagoons that produce biogas. In this case, they produce large amounts of waste, and the biogas can be reintroduced to the anaerobic digester to produce biogas. This will make, the loss existing requires for the companies to clean their waste, and with the help of anaerobic digesters, they can produce lots of biogas and making these projects very feasible. On the brewery, it's almost the same thing. They require on the jackets to heat the reactors where the beer is made. They require kind of a hot temperature in order to produce the alcohol on fermentation. So they require steam, they require hot water, and absorption chillers because they need to cool it down, just as in milk. On the bottling plants, they can have what's called tri-generation, and because the engine produces, by the combustion of the gas, CO2, the CO2 can be reintroduced into the carbonization of the beer. And also, they require steam and hot water. On juice processing, the CHP is required, again, because they need to pasteurize the juices, and the steam is required for that purpose. Hot water is also required for sanitation purposes. On the canning industry, where food is canned, the sterilization of the cans need large amounts of steam, and the steam is lost during that process. So hot water is required to be heated just as the other ones. And then last is the produce processing, where CHP is needed basically to produce electricity and absorption chillers in order to cool down the produce and put it in cool environments. Now let's go into the product arrangement. This is a typical rendering for a CHP plant. This is actually a rendering for an actual project in which two 3.3 megawatt engines were placed in a dual Hersig or heat recuperation steam boiler. There is a third bay that it is open for expansion. So you can see there that the Hersig is producing the steam, and obviously the green engines are producing the electricity, and somewhere in the top is the heat exchanger for the hot water. This is a simplified cogeneration or CHP process diagram. In this case, it is for two engines producing 6.66 megawatt electric. They are exhaust gases are equivalent to almost 82,000 pounds per hour at 680 degrees Fahrenheit. The Hersig produces 6,000 pounds per hour of steam at 9 bar. Also, we utilize the jacket waters coming out of the engine, and they are cooled down to from 194 degrees Fahrenheit to 158 Fahrenheit, and that produces hot water at 185 degrees Fahrenheit, approximately 670 gallons per minute. That one is injected into the Hersig to produce, obviously, the steam, or is directed to the aerator or the aerator tank to feed their conventional boilers. So this is the income of the yellow line is the income of the natural gas or biogas, and 6.53 is the net power. You have voltage and synchronizations and frequency losses. Very well. I encourage you to write in the questions and answers for anything that you might want to ask. The case studies. This is a poultry processing facility in which they are using the waste to produce biogas on a covered lagoon. This is an actual project that produces 1 megawatt per hour with a J320 engine. So more or less, they produce electricity and hot water for processes, and they get approximately $900,000 per year savings. Obviously, in summer, it's more, in which they can even receive up to $150,000 per month. It has a 82 total system efficiency, and emissions reductions are 50,000 tons per year in CO2. It is a very well designed and thought of project. Fresh Pet is a company that produces feed for pets. It is on a PPA or purchase power agreement, and they save on the purchase power agreement up to $100,000 annually. So you have to include also the profit from the PPA administrator. So in this case, it's a J420, or that produces 1.4 megawatt hour of electricity. It has combined heat and power producing hot water and steam. It was a turnkey project, and the facility was, or is, 58,000 square feet. And the project objectives were carbon reduction and reducing operational costs. In California, Fresh Venture Foods, this is a produce packaging facility in Santa Maria, California, and it has a J312 with a power of 633 kilowatts. The great thing about this one is that they use an absorption chiller with ammonia, which can produce temperatures of minus 40 degrees. So this is great for freezing. Obviously, the benefits were lower fixed energy costs. They had operational flexibility to adjust the right time for the pricing, and increasing energy efficiency. So they have an overall efficiency of 81%. This is another view of the engine of the J312. The box in the left is the absorption chiller, and the plant uses exhaust gas in order to produce the chilling needs, and the hot water for the other processes. So it's a tri-generation venture. Owensboro Grain is not a CHP plant, but it's an example of resiliency. They operate in island mode, separate from the grid. They have two engines operating all the time, with one as a backup. So if one of the engines enters into maintenance or has a little problem, is substituted by the one in reserve. So they are completely out of the grid, and they have large savings of electricity. Although no CHP is required, because they produce flowers and from corn and wheat, so they produce flour. Also, although this is part of another webinar, but it's well to mention it. We have many engines on greenhouses, helping them during the winter with lights and obviously heating needs, and also the engines with the utilization of SCR, they produce clean CO2 as an atmospheric fertilizer. So these are very nice operations in which they save lots and lots of electricity from the grid and heat and gas for heating. Last, we have the Miller's Coors Brewing. It is fed with biogas from an anaerobic digester for 2 J312s. That amounts almost to a little more than a megawatt. And they save almost $1 million per year. They have improved sustainability and resiliency. With this, I change hands to Christian. Christian?
Thank you, Luis. So, to finish up the presentation before we get into the question section, and please put in more questions if you have here, because we'll still have about 15 minutes at the end to talk about it. So again, to round it off, basically looking at the process of putting in a CHP. Obviously, we have a lot of experience, as we said, in this application. What we do is we first start with a feasibility study. So we analyze the on-site power generation strategy, which will deliver the most efficient and cost savings solution for you. Then we are part of the design and development, where we do the detailed cogeneration engineering and equipment design, as well as the CHP equipment sourcing, and a cost-benefit analysis to determine the best technical solution. We are part of the delivery and installation of the units, so we do the complete project management, including the delivery and installation of the equipment, as well as we can assist with the coordination with the local utilities. And lastly, most importantly, really, is the maintenance plan, because obviously the engine is only as good as the maintenance is, which supports it. So we design a maintenance schedule to really match your needs, to protect your investment and keep the engine running efficiently. Here in North America, we are basically very well spread out across the continent. We have a hybrid model where some of the areas are served directly through INNIO. That is the kind of light purple area here, which covers most of the continental US, where we sell and service Jenbacher products directly. That would include myself and Luis as sales managers. Then we have our very much valued channel partners, Northeast Energy Systems, which is in the northeast of the US, and in the western part, it's called Western Energy System. They're both part of Penn Power, as well as Clark Energy in the Midwest. Canada is serviced by Enerflex, our channel partner there for Jenbacher. So we're well covered, and we look forward to working with you on your projects. So let's now look at some of your questions here. Mark? Oh, yes. Sorry, I forgot. I think the upcoming webinars, but I'll let you briefly mention this here.
Sure, my pleasure. So the team from Jenbacher North America is continuing to create webinars for the U.S. and Canada. Next week we'll be looking at wastewater treatment plants. Also on Wednesday at 1 o'clock New York time, December 1st is a webinar around greenhouses and grow houses. And on December 7th, we'll be looking for specific customers interested in improving the performance of their Jenbacher gas engines using some specially formulated engine oils, both for the natural gas applications as well as non-natural gas You're very welcome to join those webinars. Look for more information on jenbacher.com/America, or you can find also on our main website, which is INNIO.com, all the registration information. But at this time, I would like to thank both Louis and Christian for your presentations, and also thanks to all of the attendees for your attention. We'll move into questions and answers. If you do have a question, there's still time to enter them into the widget. But before we begin, I would like to ask you once again to complete the survey, which you'll find in the widget bar at the bottom of your screen. This just helps us to let us know how you're finding the webinar and enables us to maybe get some feedback that we can improve for the future. If you would like to have us get in touch with you right away, there are a number of ways to do so. You can let us know in the chat, quite simply, the same as with the Q&A, via the Contact Us widget on your screen right now, or by filling out a form at either jenbacher.com/America or www.innio.com. And as a reminder, today's presentation will be available in an on-demand form in just a few hours, so follow the link that you received earlier if you'd like to see and or hear the presentation again. With that, let's get into some questions and answers. Well, one I've just answered. Yes, can we get this presentation? As I mentioned, the presentation is available via streaming, so on demand, via the same links that you used to join today. If you run into any issues, please don't hesitate to get in touch and we'll make sure that you get the material. So let's see. Let's start with this one. In a tri-generation project, can the absorption chiller be supplied by Jenbacher also? Louis, Christian, would one of you like to take that question?
Yeah, sure. So typically when we deal with absorption chillers, we work with a number of different suppliers. So there are different absorption chiller manufacturers. Obviously, they have different technologies. Some use exhaust, some use hot water, or a combination of both. So we try to basically look at which technology might fit, and obviously also, what temperature levels you need. So we try to assist in the technical selection process. As far as supplying the chiller, if the customer wants to, then we can incorporate that. I mean, the chiller is not manufactured by us. We source it through our suppliers. But if you would like to have us do an overall project, which includes chillers, we can do it. But you're also welcome to source it directly, and we'll assist you with the selection and sizing.
Okay, super. Thank you, Christian. The next question. So far, all of the discussion on air emissions has focused on CO2 reduction. However, NOx, VOC, and CO emissions are important, especially for facilities located in non-attainment areas. Do you provide controls for those pollutants?
Yes. So depending on where you are, and always the first question we always ask is, what emission targets do you have? So we then look at the raw emissions of the engine, which, since these are lean burn engines, they already put out low levels of NOx, and there are ways to adjust it. So in many cases on the side of NOx, we're actually fine, just as the engine goes. On the CO and VOCs, you would add a oxidation catalyst, which is relatively inexpensive and easy to do, and is basically a standard piece of equipment which most sites will use. If you then do need to go lower on the NOx side, you can add an SCR catalyst, and that's also something which we can supply. And that can be sized, again, for your application and for your location. There are different reduction levels. Common are 80%, 90%, 95%. And there's obviously a cost difference associated with what reduction level you want, both on the operational side, where you need to have urea, and obviously the equipment itself. So we have numerous ways how to take care of those three pollutants. And again, we size it right for your installation. Obviously, emission requirements in the U.S. vary a lot from place to place. In California, you would have very stringent emission requirements, and in other parts of the country, maybe less. And also, it depends on the size of your installation. The more engines you have, the more emissions you put out in total. so you might have to do more. So yes, emissions are one of the most important topics for every project, and we certainly assist with the selection of appropriate after-treatment technology.
Super, thank you, Christian. While we're talking about emissions, here's a question very similar. Have you looked at CO2 recovery from the exhaust?
Yes, we have. And it is a technology that has been applied in greenhouses and bottling companies for about 25 years now. So yes, we do CO2 or exhaust gas cleaning to CO2. There are several levels of purity. Obviously, the higher the purity, the more expensive the equipment is. But if you're looking just for a regular CO2 that is non-toxic to plants, it is very feasible and relatively inexpensive. And it is used in, as I said, in greenhouses. It's an SCR that cleans up the exhaust gases and leaves very little ethylene concentration, so it does not harm the plants. Go ahead.
Great, thank you, Luis. Moving forward, we've got a lot of questions, but we will have probably time to get through quite a few more, so please, if you do have something you'd like to ask, don't hesitate to enter it into the questions widget. This question reads, please discuss maintenance access when the genset is in a container versus an open room.
There is if it is in a container, we have more than enough space to do the maintenance from inside, and it has both sides of the container. Doors are open completely, so it can be accessed with no problem. For all changes or even changing heads from the cylinders, there's enough space. There is about 50 centimeters on each side from the engine to the wall of the container. So big enough space to work. Also, you have the access to the control room on the back, which also gives you access into the engine, and on both sides.
Okay. Thank you, Luis. Moving forward, are the exhaust emissions from a CHP system counted separately from the emissions produced by food cooking and processing equipment?
So, yeah, they are counted separately.
They are counted separately.
Mm-hmm.
Okay. Super.
Or do you have any perspective, Christian, on that one?
No, I would say that's I couldn't add much to that, unfortunately, based on my knowledge. But if we need to provide more, maybe we can look into it.
Mm-hmm.
Okay. Is a question regarding how many CHP installations does Jenbacher have in North America?
Well, as you said, 1,000 and counting.
Yeah, there's 1,000 delivered engines across North America, more than 1,000. The majority of them are CHP. I don't have an exact figure, but yeah, quite a few.
I can provide one other interesting bit on that. So about half of those engines are natural gas, and most of those run in CHP. And the other half of those delivered engines are on biogases, and that could include landfill, wastewater, digester gas. And again, if you're talking about wastewater sites or digester applications, then it's also CHP. A landfill would typically not have CHP as there's no thermal need. So you could probably say at least half, if I would say at least half, probably more than half of the engines run with heat recovery. That's a general assessment I would make.
There we go. Perfect. Next question, are there any special considerations due to cleanliness when using CHP with food and beverage processes? Good question.
Yeah, very good question. Usually the engine room is separate from the process halls or process buildings. So, but usually the engine is very clean if it's well maintained. It's a pristine engine, very beautiful engine, and it has their own quarters separate from the process. So it won't mess up the cleanliness or contaminate anything. It is completely in a separate location, and the engine on itself, if well maintained, will not pollute anything.
Okay, super. Let's see, we've got a few more. Again, if you have a question, please don't hesitate to enter it into the questions widget. For the gentleman who was facing some frequent interruptions and asked if we would share the recorded presentation, again, the presentation will be available on demand just a couple hours after this live meeting, and you should be able to access it using the same login details that you used to join this meeting. So hopefully that will work out. If you get into any trouble, please don't hesitate to get in touch, and we'll make sure that we get you the information. Here is an additional question. Does California treat emissions limits differently for CHP projects versus other power gen applications?
Yeah, that's a good question. They may, and I'm honestly not the market expert on California. We have our partner there, Western Energy, who would be the best to ask. But generally speaking, most projects in California require an SCR, and definitely all of them running on natural gas. So there might be some consideration for it, but especially if you're on natural gas, you will definitely still need an SCR to qualify under the best available technology, which is the BACT, best available control technology, which considers an SCR for NOx reduction on a gas engine.
Okay, thank you, Christian. Here should be a simple one. What does Jenbacher's team in North America look like, or does everything come from Austria? I think this is an easy one for you to answer.
Go ahead, Christian.
Yeah, so we have a very diverse team here in the U.S. As Mark alluded to, our headquarters is Houston. That's where I'm based. Luis is based. We have a good team of application engineers here, commercial operations, service managers. And then obviously we also have people spread out throughout the country, either working directly for Jenbacher, servicing our engines out in the field. Throughout the country, I think we have over 25 technicians now spread out over the country, and of course our regional distributors in different parts of the country. So very much the sales and service support structure is North America based, and definitely also don't want to forget Canada, where we also have Enerflex, and we also have some of our own INNIO employees working in Canada. The engine itself, or the engine generator set, comes out of Austria. We also package in containers in Europe. We have different packaging facilities there. If you choose to have a containerized system for outdoor installation. However, here locally, we then complement those solutions with balance of plant, electrical switch gear, anything that's really needed, depending on how much the customer wants to have from us. So there's always quite a bit of a local component, and most definitely, obviously, service is local. We have parts storage in the U.S. and our technicians here, so that's all definitely local. So it's really that mix of the equipment coming from Europe, but a very local team here to support it.
Excellent. Perfect. Couple of more have come in. This question reads, will SCR be required if a gas-fueled unit would be used for standby applications? Maybe I'll repeat. Will SPR be required if a gas-fueled unit would be used for standby applications?
As always, the answer is it depends. So if it's only for backup power, then typically your emission requirements are lower. But many of the units we put in, they are not only intended for backup power. And even if you use it only for backup power and the installation is very large, the emissions of all the engines do to add up. If you then also want to use it for non-backup power needs like peaking, and that's one of the main reasons people choose gas engines over a diesel engine. A diesel engine can typically only be used for backup power, but it can't be used for peaking applications unless it has a very high emission reduction level. A gas engine you can use for peaking applications as well. And then again, it depends on the number of run hours you would put on the engines. You look at the total emission output and the size of the installation, and then you may or may not need an SCR. So we have plenty of sites where people use these as peaking units, which run for, let's say, 500 hours, 1,000 hours, which don't have any SCRs. And they also use them as backup power. But then again, if it's a very large power plant, then overall the emissions add up where you do need to potentially put in an SCR. So it's very case by case.
Super. Thank you, Christian. We have a few more questions here. Again, if someone has a question, please go ahead and enter it into the chat. If we don't get to your question, we'll do our best to come back to you as soon as possible via email. This question is reading, for the J320, what would be the overall efficiency, and can you please break down into each individual component, power, steam, absorption, chiller? Maybe start with overall efficiency.
You want me to do that, Luis, or you want to do it? I'll do it, I guess. So the efficiency of a 320, let's say a typical 320, let's say you're at electric efficiency of give or take just below 40%, let's say 39% electric efficiency. Then on the thermal side, depending on what type of heat recovery you use, but let's say hot water, you can get a lot of hot water out of it to then reach a total efficiency of 90%. So basically, you're adding about 50% of thermal heat recovery to the just under 40% electrical to get you to 90%. If you're using an absorption chiller or a steam generator, then your overall efficiency drops below 90% just because you can't recover that much heat. There's more wasted heat for absorption chilling or steam generators. So the highest total efficiency you get if you do hot water, and then if you do steam or absorption chilling, you might drop a bit below 90%. But that's as a rough ballpark where you are, somewhere typically between 80 to 90% are most CHP applications.
Great, super. And what I think will be our final question as we're getting down to the final minute. Does anyone ever recover heat from the auxiliary circuit or only the jacket water?
Yeah, what we have is a hot temperature circuit and a low temperature circuit. What we are usually talking about is the hot temperature circuit where we mostly recover all the heat. But yes, there are instances in which the low temperature circuit is used to recover heat. It depends on your needs and the temperatures required by the customer. But yeah, it can be used.
Okay. Thank you, Luis. I think we are coming into the last 30 seconds and we've reached the end of today's webinar. Again, if we did not get to your question, we will do so via email as soon as possible. Please remember that today's presentation is available on demand, so feel free to visit the platform and listen or watch again if you'd like. And you can also share today's webinar with others. On behalf of Christian, Luis, and Jenbacher North America, thank you for joining today's webinar on solutions for food and beverage. We hope you found it interesting, and we look forward to speaking to you about how Jenbacher gas engines can support your CHP projects soon. Thank you, and have a very nice day.